But chapter 16, we start looking at the amines as bases. We already started this. Here's ammonia. The pKb is 474. Here's bromamine. The pKb is 761. And again, it's a power function. And so this has about 3 orders of magnitude difference. And it turns out that the smaller the number, the more basic it is. And so it looks like bromamine is about 3 orders of magnitude, 3 powers weaker. And so that would be 1,000 times weaker, roughly. Why is bromamine so much weaker of a base? What would you say? Yeah, Br pulling the electron. Br pulling the electron density away from nitrogen, making the nitrogen less basic. So this nitrogen is going to be a lot more basic, 1,000 times more basic than ammonia. That would be an example of inductive wood drawing. Here we looked at some of these the other day. Actually, this is the wrong number here. 474 is right for ammonia. This one has, what would you expect? Methylamine. Should it be lower or should it be higher? It should be lower because lower is more powerful, right? And we said that the methyl groups are electron withdrawers or electron pushers? Electron pushers. So if this is pushing electron density towards the nitrogen here, that's going to make it more basic. And we can see it's going to be an electron pusher based on its oxidation state. What is the oxidation state on carbon? Minus, in this case, -2. If this were a carbon, it would be -3. But this is nitrogen, so nitrogen takes off. So this is -2. -2 is pretty electron rich. What would you expect ethylamine to be? Ethylamine, to be more basic than methylamine or less basic? More basic, the chain, the chain. And you saw the chain length makes a small difference. It's not going to be hugely more basic. But, what we'll do is we'll take a look at some data here from Appendix D. Just log me out again. All right. These numbers are just the regular linear, not the power numbers. So these numbers, the bigger this number is, the Kb, the more basic it is. So ammonia, 1.8 times 10 to the minus 5. Methylamine, 4.2 times 10 to the minus 4. So it looks like methylamine's about 10 times stronger, roughly, than ammonia. And so if we go from methylamine to dimethylamine here, we go from 4.2 to 5.9. So dimethylamine would be stronger. And so having 2 of those electron pusher groups can make the nitrogen more basic. But what if we have 3 of the electron pusher groups? You would expect it to be more basic yet, right? And so we go with 3 electron pusher groups, trimethylamine, and it's 6.3 times 10 to the minus 5. Well, 10 to the minus 5, that's like 10 times smaller. In other words, it just got weaker. Right? And so having one methyl stronger, two methyls even stronger, but three methyls weaker. And so sometimes this happens. Actually, this happens a lot more than you might think. You know, in science, you know, like Chem 4, how everything works perfectly. When you actually do research in science, you know, there's stuff that, you know, you have this beautiful correlation, and then all of a sudden you take a couple more data points and it screws everything up. And so what should you do? You know, well, one thing is we could just kind of ignore this. That's often done. You just ignore it because it gets messy. You know, this works so nicely, right? But all of a sudden, when we get to 3, it makes sense that it should work. And so a lot of people just ignore it. But you know, there's a point you can't ignore it. In fact, there's a very famous very famous news story that happened recently. I think it was like 5 years ago or something. It involves a Nobel Prize winner too. One of the researchers working under this Nobel Prize winner was collecting data, and a few of the data points caused headaches. And so what that person did was they deleted those data points from their. Yeah, that's an easy fix, right? A very easy fix. But it turned into a big tragedy, actually. A really big tragedy, because one of the people actually ended up committing suicide. But anyway, yeah, you know, it's obviously we can't get rid of the data. I mean, the data is there, and so what do you do? Then, you know, this usually happens. You know, everything's going along, and then this usually happens with a deadline. Like, oh, you have to present the results of your findings in a week. And all of a sudden, this throws a wrench. You know, oh, I knew what was happening, and now I got a wrench thrown in, and it's all broken down. Now, what do? You know, delay. Yeah, I want to postpone or cancel my talk now. That happens. Yeah, people postpone and cancel. But the thing is, you know, it's kind of everything seems to work. As you'll see, like when you take pH measurements and stuff like that, you know, what you calculate is way off from what you actually observe. And then why is that? Is it because the calculation's wrong? Is it because the meter's wrong? Why is your calculation so far off than what's observed? You know? And then somebody's going to ask you, why is your calculation so far off from the observed? And what are you going to say? Well, you know, it worked so well in Chem 4. You know, all of my calculations worked out perfectly. Well, they worked out perfectly because, one, they either get rid of the ones that don't work, or two, they never actually compare your calculated value with an actual experimental value, right? And so things get more messy. And so what should we do? Well, today, you know, what we're going to do is this. We're going to, you know, there are probably multiple factors. You'd say that, well, there's got to be additional factors that impact the basicity, just like acidity. And so what we're looking at today in today's lab is we're going to try to correlate acid strength with polarity, and just polarity alone, you know. And so we'll see how that correlation is. And then I'm going to have a supplemental lab. The supplemental lab is going to be with the amines here. And you can see if we can figure it out. But the situation is this, you know, when you're actually working in science, then people, you know, it's not like, oh, you know, that calculation didn't work out well, and going to ignore it. But, you know, when you're actually working, you have these headaches that come along once in a while, where things don't, or things are more confusing than what you thought. Well, this one shouldn't be too confusing. This one should work out nicely. And so as we go along, we see that something like this, aniline. Aniline is a much weaker base or much stronger base than predicted. Aniline's a much weaker base than predicted. And it has to do with this. This is this benzene ring here. Because if we look at cyclohexylamine, if we look at this, this is a 6-membered carbon ring. These are all sp3 carbons. And we look at the base strength, it's pretty basic, you know. And that's because this is a hydrocarbon group. Hydrocarbon groups are known as electron pushers. Hydrocarbon groups are electron rich. Right? So this is electron rich. This is also a hydrocarbon group, but when we look at the basicity, that's 1,000,000 times weaker. And that is, cyclohexylamine is 1,000,000 times stronger of a base than this. Does that make sense? And it turns out it does make sense because of the ring. This is a special ring. This is what we call aromatic ring. And benzene isn't the only aromatic. There are lots of aromatics out there. But because of this ring, then we did this the other day. These are all the resonance forms we can draw out for this, where we can delocalize the charge within the ring. If we look at the orbitals too, using valence bond theory, that we'll see that the lone pair here can be delocalized into the pi bonding network here. Okay, now let's say if we put a chloro, this would be in the para position. If we put a chloro in the para position, does it weaken or strengthen? It weakens. Does that make sense? If we put a chloro in the para position, that is, this is parachloroaniline, just a chlorine atom stuck there, that it would weaken it. Yeah, that makes sense because yeah, it pulls some of the electron density out. And the same thing here, a chloro in the ortho position. But what about a chloro in the meta position here? Chloro in the meta position wouldn't make that much of an impact. So we should have that in there. Now there are some differences there. You know, if you're working in science, the people are going to ask you why the difference here. Because it looks like that para is about 10 times stronger than ortho. And you'd have to come up with, you know, either I don't know, or, you know, you'd have to come up with some sensible argument why. All right, the final section of chapter 16 deals with Lewis acids and bases. A Lewis acid like this is just capable of accepting a pair of electrons. Boron trifluoride, it turns out to be a powerful Lewis acid. It's a powerful Lewis acid because it's got less than an octet, so it wants to complete that octet. And so what happens here is an sp3 lone pair comes in. There's an empty p orbital. This is sp2, empty p orbital. We have an sp2p overlap, and then it's going to hybridize to sp3 to minimize the repulsions. So we have this. This is called the Lewis acid-base adduct. For Lewis acid-base reactions, we need some orbitals, or they could also be filled. I got to kick electrons out. But when we look at the acidity or basicity of Lewis acids and bases, it's complicated because do you see BF3 on your acid table? BF3 is not on your acid table, as are a whole bunch of other Lewis acids and Lewis bases. And so the way we determine what's a stronger one is this. It depends on how it's paired, and how the orbitals, either, there are two ways of thinking about the orbitals, because here I have an sp3 on the nitrogen coming into a p orbital on boron, and this empty p orbital here. Right? And so the way we think about how the orbitals pair is how they overlap. If there's good overlap, then it's strong, right? If there's poor orbital overlap, then it's not good. That is, if one, let's say, the best match is if one of these species has an orbital like this and the other species has a comparable orbital, and then we get good orbital overlap. And so in other words, if we have a small orbital and a small orbital, that's good. However, if we have a small orbital with a big orbital, it's not so good because the orbital overlap and the linear combination of atomic orbitals form molecular orbitals isn't as energetically favorable. However, if we have a big orbital and a big orbital, that turns out to be good. And so big orbitals are what we call soft, polarizable. Electron clouds can distortable. And so if something has a big orbital, we call it a soft species. If something has a small orbital, we call it a hard species because the electron density is more concentrated, it's harder to distort. And then to better understand that without having to do, because otherwise we have to do quantum calculations. To understand this, to predict using pencil and paper, we use something called HSAB. Does anybody remember what that acronym stands for? I know it's been a long time because the first time you heard HSAB was like the first week of school. HSAB. Or maybe I didn't. I don't know. It's been a long time for me. Maybe I made no mention of HSAB. Well, let me tell you what HSAB is. Yeah, if you Google it.
Part of the soft acid on base.
Yes, that's it. What happened to my HSAB, not HASB. HSAB. Ah, that's on Wikipedia. That's good. HSAB is a way of predicting the strengths of Lewis acids and Lewis bases. And not necessarily strengths, because some acids will be strong to only specific species and weak to other species. And so if you have a hard acid, then a hard acid wants a hard base or a soft base. A hard acid wants a hard base. So that's a reactive combination. And so you might say, oh, the hard acid, that must be strong. Well, no, not necessarily, because if you take that same acid and try to react it with a soft base, it doesn't work so well. And so hard, soft acid base deals with orbital overlap, or orbital overlap would be for valence bond theory, or with linear combinations of atomic orbitals for MO theory. And so Ralph Pearson is the guy who developed this, and the nice thing about this is you don't need a computer to do this. You can make predictions without. And so here are some examples of hard. So for example, mercury is a soft, so mercury would much prefer sulfide. I asked you which base is, did I ask you which base is stronger, sulfide or oxide? I think I forgot to ask you this. I asked in the morning classes. Sulfide versus oxide. Which base is stronger? Oxide, yeah. Actually, Z. I know Z's asking me about. Yes. Oxide's stronger. Why? Than sulfide.
Yeah, because it's smaller.
Because it's smaller. Sulfide is bigger. That's why. Oxide's more basic because it's smaller. That means the charge is going to be more concentrated than sulfide. And so, but we have to qualify this. This is for Bronsted. The thing about Bronsted, the acid atom's always the same. In Bronsted, all Bronsted acids have a hydrogen. Right? But in Lewis, they don't. Lewis, we can have a whole variety of acids. And so, in terms of Lewis, which one is stronger? I don't know. Because oxide is hard or soft? Hard. Sulfide is soft. So which one's stronger in terms of Lewis? We don't know, because we don't know what we're reacting it with. So, for example, if I'm reacting with mercury, then mercury would much prefer to react with sulfide or oxide. Much prefer sulfide over oxide. And so sulfide is a powerful base for mercury. However, if I'm reacting it with, let's say, chromium-3, then you would probably say, well, chromium-3 is hard, so I probably would react it with oxide. Oxide would be a better. And so Lewis, unfortunately, is quite a bit more complicated than Bronsted. And so, and Lewis, this hard, soft, acid, base stuff is beyond. The book doesn't even mention this, right? And this is beyond the scope of this class, but this is why I never really talked about Lewis acids and bases in detail. I only talked about Bronsted acids because, you know, I don't want to get into this because this will take too much time to discuss. But when you're dealing with Lewis acids and bases, you have to get into this. So, for example, carbon monoxide. What kind of base is carbon? Carbon monoxide is a soft base. So, in borderline cases, etc. Here's some. This is all based on quantum mechanics. And there's something called Mulliken's electronegativity. You know the table you guys have been using? You know what it's called? The electronegativity table you guys have been using is called the Pauling's electronegativity table. And this is why I keep saying, you know, the Pauling's, the electronegativity is just kind of a guide. It's not really realistic. The Mulliken electronegativity table is much, much more detailed. Let's see if we have the Mulliken scale here. As a real table. Okay, this is still not very detailed. This is only part of it. As we go on, you'll see it depends on, well, there are more, and you don't have to worry about Mulliken's electronegativity. There are more detailed electronegativity tables. They'll give you a much more accurate number than what we've been using. So this is why I don't take too much. But anyway, we have Lewis acid-base reactions, and Lewis acid-base reactions, all Bronsted acid-base reactions can be considered Lewis as well. And here's another example. Here, this would be solid calcium oxide reacting with sulfur dioxide gas. So sulfur dioxide gas would come into contact. So this sp3 lone pair would get pushed in here. Well, this is an octet. Let's see, 2, 4, 6, 8. Yeah, it's bent. And so this would get pushed in here, break the pi bond network, and create something like this. Here we got to look at how the orbitals interact. So this is calcium oxide reacting with sulfur dioxide to make calcium. What's that? It's calcium sulfide. This is calcium sulfide with an octet, no expanded octet. We could expand the octet, get rid of these formal charges here if we want. But again, there's all right. This is also an example of a this species here comes from a Lewis acid-base reaction. The Lewis acid-base reaction is, it turns out that aluminum 3+ is a Lewis acid. And then water is a Lewis base. So what happens is this sp3 comes in here and bonds here. Now, what we end up with is this. We end up with a covalent bond here formed between the water and the aluminum. And so we end up with a species like this. This type of reaction we talk about in Chem 1B. So I'm not going to spend too much time talking about this. But how does this work? I mean, what orbital does this go into? Here. And it turns out that valence bond theory fails for this kind of reaction here. we have to use molecular orbital theory to describe this. And so a lot of people will say, oh, you know, the aluminum's sp3 D2 hybridized. Well, it's not. We've got to look at this. But anyway, the aluminum 3 plus, which is a Lewis acid, can actually react with 6 waters. And this is an actual covalent bond, although it's not, you know, extremely strong. That is, something can come over here and hit the water and knock off the water and break this bond. That's possible. And so this is not totally inert. This is called a complex, but nonetheless, this can happen here. It can actually bond to form this species. Now, this species itself is a Bronsted acid, because what happens is this: aluminum's 3 plus, and so what it's going to make, it's going to make these hydrogens much more acidic than they normally are in water. You know, these hydrogens aren't all that acidic. Water, very weakly acidic. But here, this is pretty strongly acidic. In fact, that species there is acidic as acetic acid. And so aluminum 3 plus dissolved in water will be as acidic as acetic acid. Here we can see how this reacts. So we got these water molecules bonded on here. And this whole thing's called hexa-aqua aluminum 3 ion. And so here's a water acting as a base this time. It's going to come over here. It's going to be attracted to that proton. So this sp3 gets pushed into the S. Here we can talk about valence bond, but here we can't. And kicks out these sp3. And so we end up with this in hydronium. And so what this does is it makes these aluminum salt solutions acidic. So aluminum chloride is like an acid like acetic acid. You know, it's pretty much just as acidic as acetic acid, which is weird. Well, what about sodium chloride? Well, sodium chloride doesn't quite have the charge required to bond like that. Aluminum is highly charged and is small. So highly charged and small species turn out to be quite acidic. So in this table, we see just a jumble of data. So for example, here we see aluminum 3 plus. Here's its size. It's 53 picometers. Here's its charge to size ratio. That is, it's 23.8. This we can think of as charge density. So the higher this number, the greater the charge density. And so here, and then we see the pKa, the power of the acid. The smaller this number, the more acidic it is. And so this looks like just a mess of numbers here, but we have to try to sort this out. And so here we have aluminum 3 plus. I told you it's as acidic as acetic acid. Acetic acid has a pKa of 4.74. Aluminum 3 plus ions has a pKa of 5.0. Very close. And so aluminum 3 plus is quite acidic. What else is quite acidic? Chromium 3 plus in water is quite acidic, 4.0. Titanium 3 plus, 2.2. Iron 3 plus, 2.2. All these species have pretty high charge densities. If we look at lithium, sodium, potassium, these have very low charge densities. And if you look at the pKa's are orders of magnitude larger. And so if the pKa of aluminum is 5 and the pKa of potassium ions is like 15, that's 10 orders of magnitude, which is like 10 billion times weaker. In other words, aluminum 3 plus is 10 billion times stronger of an acid than potassium ions are. And so what we say are potassium ions, sodium ions, lithium ions are neutral in water. Beryllium 2 plus is not. Beryllium 2 plus is quite acidic because of its size, right? Magnesium 2 plus is not. Magnesium 2 plus is pretty neutral. Do you see that? It wouldn't be very acidic at all. And so we can see that a lot of these metal cations are quite acidic. And so what we try to do is we try to look for a pattern. And how does this pattern look to you? And so this pattern is plotting the power of the acid strength versus the charge density. Does that look like a good correlation to you? Well, you know, if I kind of ignore these points, then it looks like a decent correlation, doesn't it? It looks like the higher the charge density, the stronger the acid. the pKa is going down. So that looks like a pretty decent correlation. But then what's going on with these? So it looks as if there must be other factors involved as well. Of course, there are. And so we've got to figure out what these factors are. But what we can do is we can just generally summarize. You know, once the charge density hits a certain point, then these are all pretty acidic as far as cations go. And that makes sense. Obviously, the higher the charge density here, the more polar you're going to make these. But, you know, it's this kind of, like some are maybe some are usually acidic, or some are less acidic than you expect. You know, if you're looking at some kind of trend like this. You're looking at a trend like this, we have some outliers here. Like these are unusually acidic, and these are not as acidic as we would expect. Well, there's some reason for that, you would think, right? I'd like to find out what that reason is. Well, you know, this is it. This is the scientific method. The scientific method is this is the jumble of data, and you got to sort through it. And you sort through it, and sort through it, and sort through it. Unless a lot of people say, oh, no, the scientific method starts off with a hypothesis. Well, tell me your hypothesis, you know? It doesn't really start off with a hypothesis, because how do you generate a hypothesis? You generate a hypothesis by knowing, you know, some observations. If you don't have any observations, what kind of hypothesis you can tell me? Well, maybe you could have hypothesized, but when we do hypothesis, we want numbers. I want numbers. You know, I don't want, yeah, that's going to be a little bit more acidic. I want to know how much more acidic that's going to be. And so can you hypothesize that, okay, if I replace this with a beryllium 2+, tell me how many more times less acidic or how many more times more acidic it's going to be quantitatively, you know? That's not easy to do, of course, right? But anyway, what we do is we just take a whole bunch of just seemingly random numbers here, and we try to sort through these. And if you looked at this, you know, it does seem totally random. It seems like there's no correlation there whatsoever, right? If you look at this, there appears to be some kind of correlation with some outliers here. Or maybe this is the correlation, and there's a whole group of outliers here. But it doesn't seem like that, because once we hit this certain point here, or maybe this is properly correlated. Maybe there are multiple factors. And so these are the types of things we think about in science, because this is typical. You know, you get some data, and the data looks like this, and what do? 1 week later, you have a conference. You got to explain to everybody what all this means. Can you? You know, and that's a situation you don't get much in chem, in intro chem, because everything works out so perfectly, and if it doesn't, they just omit it. So you don't have to deal with messiness, you know? Okay? But you get a messy chart like this, and you go, I don't like that. And so this is why people get the white out, and white this one out, white that one out, white these one. And then they set up some storm of controversy. You know, why are you deleting those data points? So that's what happened, actually, to that. They had a reason. They're saying they're just cleaning it up so it was easier to see the correlation. But it was quite a famous story. You can look it up on the internet. But you know, there are other instances of that. But you know, things can get messy once you start dealing with real numbers, for sure, compared to just and especially real numbers that you're held accountable for. You know, why doesn't your number work? And so those are the types of things. And that's something that that's something that was a bit of a transition for me, a bit of shock for me, because when I went through my undergrad, you know, I expected everything to work out properly. Science, right? Like Newton's laws. You know, Newton. You can, when you're calculating acceleration or position or whatever else, you know, they can pinpoint these things. They got these satellites. You know, if the satellites are off by a few millimeters, you know, in their trajectory, that can translate to a long distance, you know, and if it's traveling far, you know. But what about your calculations in chem, you know, or whatever, biology or whatever you're doing? And so, okay, so I'm going to stop here, and we're going to do a tutorial from